Hi guys, happy Thanksgiving. First of all, I wanted to thank the four of you for agreeing to do this with me. I saw it and I thought it was a super cool opportunity to travel and get acquainted with quantum computing, which is something I don't know much about, but maybe we can learn together. My goal is to learn from this IBM lecture series that I'm following, which goes through classical information and quantum information and bridges the gap. It goes from single state systems to multiple state systems, which I don't really know the meaning of, but we'll learn together. And my goal is to condense as much of the time in there into these short videos so you guys can learn as well. So this video will be the first 20-ish minutes of the first video, which is on states, classical states and probabilistic states. But my goal for the lecture series, this series, is to go from classical information to quantum information and then maybe mix in a little bit of hardware. This competition is mostly coded in Python, which I think most of us are familiar with, so that shouldn't be too much of an issue. It's just the quantum computing knowledge gap that I'm trying to fill with this. So yeah, this lecture series mostly goes over classical states. So it defines a state X, which can have all sorts of states. Anything you want, on or off. If you have a six-sided dice, a die, it can go from states 1 through 6. But for the purposes of this, let's just say you have a system X, which has two states, 0 and 1, like a bit in a normal computer. So yeah, you in this system, you can either have 0 or 1. And the notation that this introduces, which is very widely used in quantum mechanics, is the ket notation. So ket, K-E-T notation, which essentially describes you can either have 0 or 1. So for any state alpha, the ket notation it's described like that. So if you have ket 0, that describes the 0 state. And if you have ket 1, that describes the 1 state. And now these ket notations can be described as vectors as well. So the 0 vector, ket 0 is also equal to 0, or actually 1, 0. Because in this state, the first possible state is 0, the second possible state is 1. So since this is in the state 0, it has a 1 in the 0 spot and a 0 in the 1 spot. And if you have ket 1, you are equal to this. This is the vector that represents this state. So yeah, let's say you flip a coin and it lands on this. Then you could represent heads, for example, heads or tails. You could represent the heads as 0, and then that would be represented as this sort of vector. Now, let's say you have a coin that is weighted, so it's not even on either side. Instead of having a 50-50 probability of landing on either the heads or the tail side, there is a 3/4 chance it lands on the head side. Let's say it has 3/4 of its weight on the head side, and a 1/4 chance of landing on the tail side. It has 1/4 of the weight on the tail side. Now you can represent the total probability of this system happening as 3/4 of ket 0 plus 1/4 of ket 1. That's just kind of the way to represent this. And in the classical system, there's not really a probability of everything happening. And once you observe the result of this system, if it landed on heads or 0 or tails 1, then it becomes, it is in that 0 state, or it is in that 1 state. But yeah, basically the idea of this video is ket notation. So right here, the idea that any state, it can be represented as alpha and alpha is the state, and the system, the system of the state is ket. So this bar alpha and this line here. Yeah, cool. That was the first video.